So what I thought I'd talk about today is a line of work that started several years ago related to effort-based decision-making. And if you just think about what you do on any given day, you actually make multiple decisions about what you're going to do in which it entails some sort of required effort to accomplish something. And in some of those cases, you decide, yeah, I'm going to do it. Some cases you don't even think about it in terms of a conscious decision. You just go ahead and make that effort. But there are other times, particularly when you're tired, where you're just like, oh my God, just getting up to go to the kitchen and put away my dishes seems like too much work. And so we became interested in this topic, particularly coming at it from the perspective of depression and situations where people may be so unmotivated that it's hard to expend the energy to even take care of some of the activities of daily living that they need to. My lab does a lot of work with the neurotransmitter dopamine and trying to understand correlates of dopamine functioning and what are some of the ways that modulation of dopamine impact cognition, motivation, emotion. And I had a student in the lab at the time, Michael Treadway, who was reading some of the papers of John Solomons, and John does work at University of Connecticut, and he's had a paradigm that he used very effectively in which he put mice or rats into a T-maze, and they'd have an option. They could go freely or with minimal effort and get a low reward, a smaller amount of food, or they could climb over a barrier and get a higher amount of food. So you essentially had a choice between an effort expenditure for better reward or minimal effort for lesser reward. And healthy rodents, when they do this, will predominantly choose to do the harder effort in order to get the better reward. But if you put a blockade on dopamine, so for instance, if you use haloperidol as a dopamine D2 antagonist, what you find is the rodents will not go for that harder effort as much and will instead go for the lower effort. Now, there's not a change of how much they seem to like the food. If you give them free access to the food, they eat just as much as the normal animals do. So they're unwilling to work for it, even though they seem to like it and eat just as much of it. You can also go in the other direction in terms of this manipulation. If you give amphetamine to the rodent, and amphetamine will work by causing the dopamine transporter to release dopamine instead of bringing it back into the cell. You increase your levels of extrastriatal dopamine. If you do this in those rodents, you increase their amount of willingness to work in order to get it. So we had this push-pull effect of dopamine on effort-based decision-making, and we thought that was a really cool phenomena, and we were thinking about how could we operationalize this to do something similar in humans. Of course, the first thing you think about, well, could we make them climb over a wall to be able to get the reward? That seemed a little bit excessive to us in terms of what it would take setting up a lab to do that. Nowadays, we might try something like that, perhaps with some like virtual reality. At the time, we weren't there yet. And so we just turned to another sort of paradigm that people would use to do this in rodents, where they'd have two levers, and one required more work, more presses to get a better food, and one required only a single press for the animal to get a food. And we knew that there were animal paradigms that had done this, and it generally showed something similar to what John had been seeing with his T-mazes. And so we gotta jump in slides there. So we developed a task called the effort expenditure for rewards task. And on this task, what happens is on every trial, the person basically comes in, they get shown the parameters of the task, which include a low effort option, which is just going to be tapping with their index finger a set number of times, and you get $1 if you do that. Or you could choose the hard task, in which if you sort of put your hand down and don't move your whole hand, but you use your pinky to respond and do a whole bunch of presses with that pinky. And just go ahead for a second and do it with your index finger of your dominant hand, and then try doing this with your non-dominant pinky. You can do it. You can do it. You can do a number of presses, but you can very quickly feel the difference in the effort level required to do it. So on this, they've got they know on each of these trials what that different effort level is going to be. They know the difference in the amount of reward they can get. They're also just given a probability level. If you do the task, what's the probability that you're going to get rewarded? You can see already we've thrown a few things at people that they're having to make a few different judgments simultaneously in making their decision. And we did this in part because we both were interested in some of the decision-making characteristics that might come into play. We also wanted it to be at least complicated enough that it prevented people from just like instantly being like, oh, I've already decided before I even start this task what my responses are going to be, because I've like calculated it in my head what the right percentages might be. So excuse me for just a second here, because for odd reasons, something got out of order in my slide deck here, so I just need to go to my right place here. And so we started to use this task, and one of the first things that we did with this is we applied this in a patient population with major depressive disorder. And we recruited about 20 subjects with depression and 20 subjects who were healthy controls. We ran the task, and what you can see here is in both cases, so we got our controls in blue, our depressed subjects in red. Throughout the entire range, we find that our depressed subjects are less likely to choose the harder reward. Both groups do modulate their behavior based on the magnitude of the reward. They're more likely to work the higher the reward is. But you can see that just across the board, there's a difference in that allocation. This has been replicated at this point multiple times, this finding across multiple studies, either in which there's either a difference seen between depressed subjects and healthy controls, or that the effect essentially correlates with self-report of what we call anticipatory anhedonia, or ratings of how much the person anticipates rewards or how excited they say they get in response to rewards. And so we've seen this now replicated multiple times in an era where we're always concerned about replications. It's particularly rewarding when, the initial study had 40 subjects, not a huge sample, but the finding appears pretty robust. Interestingly, it's not just that the patients with depression show a less willingness to work for a reward. They also don't use the reward parameters, the parameters of the actual task, as well as healthy controls do. So you can see if we measure this in terms of sensitivity to reward magnitude, though both groups are showing some sensitivity, there's a flatter slope that we see for the depressed subjects. The depressed subjects also don't use the information about probability as well as the controls do, again suggesting that they're not utilizing this information as adaptively in their decision making about expending effort. We can model those decisions computationally, and typically the way we've modeled this has been through a fairly simple formula of subjective value V here is equal to the amount of money that was available, subtracted by, after subtracting essentially a discounting factor. And the discounting factor is based on essentially the cost of the effort that the person's exerting. When you actually do these sorts of computational models, this follows essentially a sigmoidal function in which there are really two key things about this discounting. One is the K value, which is going to be the slope, how steeply the person is affected by the effort that's there. And the other, which is this P value, is really a turning point. If you're having to do some effort, when the effort's low enough, it doesn't really enter into the equation. There's a certain point where it starts to become, oh, that's enough work that I'm actually going to factor that in. So if we apply these sorts of computational models to decision making in depression, it's interesting. We can see a couple things that show up. Here, across the board here, what we're seeing is that, as we'd expect, the depressed subjects are showing essentially a lower subjective value rating at each different reward or effort level here. But the other thing is you can see that overall our slope is actually greater in the depressed subjects, showing a greater discounting based on the effort. They also actually have a significant difference in their turning point. And strikingly, our depressed subjects, at least in this sample, many of them started discounting immediately. Whereas for the controls, it took a while before they started. But here we had 61% of our subjects with depression, their turning point was basically immediate with any effort level, whereas we only saw that in about 5% of our controls. So we can get, using these sorts of models, we can try to actually tease apart some of these differences that are entering into this decision making. There's a clear understanding of some of the circuits that are involved. This particular figure was derived primarily from rodent studies, and many of these cases were lesion studies, and there's several areas that are clear. One is the anterior cingulate appears to be particularly affected by what the actual effort level is, but this circuit of calculation feeds down towards the nucleus accumbens ventral striatal region, where we also are going to have the ventral tegmental area with an input of the dopaminergic signal. And this ends up being a major integration site for this value coding in these sorts of decision making. When we flip this over into human data, we can actually sort of track some of this. For instance, in this study by Miriam Klein-Fluge, they show that the anterior cingulate and the SMA, the supplementary motor area, their activity is essentially coding the effort level. So as the effort level goes up, the firing in these areas, the activity in these areas particularly accelerates or increases. A recent meta-analysis of sort of all the literature, some of it using the effort task, some of it using other similar sorts of tasks, shows again that there's actually only a few areas that seem to be really specific to coding that effort level. And so we see it for here up into the SMA here. Then if you can look at the areas that code for the net value, in other words, they're coding for the value of the stimulus after integration with the effort level, you see a classic response pattern in medial frontal, sort of ventromedial prefrontal area, which we see over and over again across different sorts of subjective value studies, whether you do temporal discounting or any sort of calculation where you're looking at value, you'll see this area come into play. But we also are seeing our ventral striatal region come into play once we get to this level of integration of effort and reward value. And again, we can see the area here, which is just sensitive to effort. But you can see it's a broader area that calculates this integration or is responsive to this integration as opposed to just the effort component. So we, of course, coming at this initially from the perspective of dopamine, were particularly interested in this signal here of what happens in the nucleus accumbens ventral striatal region when we manipulate dopamine. And just at the behavioral level, we could take a look and see what happens when we do manipulations of the dopamine system. So for instance, in this first study over here, which was done with Harriet DeWitt's group with Meg Wardell at University of Chicago, we gave oral amphetamine to healthy individuals. This was done across 3 separate days. One day they got placebo, one day they got 10 milligrams amphetamine orally, and another day they received 20. It's counterbalanced, double-blind in terms of the procedures. And there are a few things that show up. First, overall, there is an effect where at the highest levels of amphetamine, the people were more willing to work and expend effort. But there's actually something really, I think, really interesting here. On the high probability trials, when it makes sense to go after it and work, it really didn't make a difference. Everyone's at a pretty high level of responding. It's really, once we get down to this low probability situation, where we see an effect, where at the lowest probability, you really shouldn't waste a whole lot of energy here. And yet this is where amphetamine seemed to really push things the most, where you did see an significant increase in the willingness to expend energy when you had pushed the dopamine system harder. I would argue this is not necessarily an adaptive thing. They're arguably, I mean, if you've got the energy to give, why not expend it? But in general, you're failing to utilize that information to protect yourself from more costly effort expenditure. You can wonder about this in psychopathology like mania, where people will actually expend lots of energy, sometimes on very improbable sorts of outcomes, and this might arguably be connected to something like that. In a later study, Meg, this wasn't in my lab, but she went and did this using a new sample, doing the computational modeling, and what you see is that if you look at that discounting factor K, it is going down. So it's the discounting that is decreasing when the person performs this task on amphetamine. So I mentioned to begin with that a big part of my lab has been studying dopamine, and the way we've done a lot of these studies has been to use PET imaging, which allows us to label different aspects of the dopamine system. And so in my own lab, we worked a lot with falopride, which is a high affinity D2, D3 ligand. And it's the advantage of it is it's got high enough affinity that it lets us measure D2 receptor levels both in the striatum, where you have extremely high levels of dopamine receptors, but sensitive enough that allowed us to also measure dopamine receptor levels in cortical areas as well, where you couldn't with the most typical radioligand, which is raclopride, which is not nearly as sensitive. And so I spent a good chunk of my time at Vanderbilt running PET studies making use of this. We also did a number of studies where we would use this technique to measure dopamine release. And the way we do this is we give falopride on 2 different days. One day would be a control placebo, and another day we would give the subject amphetamine. And what happens is when the system releases dopamine, that goes and occupies receptors. That's the endogenous dopamine occupying receptors, and that means there's less receptors that the radioisotope can then bind to. And so we can measure that difference as a proxy for dopamine release. And you can use this essentially as an assay or probe of the reactivity of a person's dopamine system. So we went and did this approach and measured in a group of healthy individuals. We measured essentially the responsivity of their dopamine system. We also, just at baseline, had measured their effort performance on the effort task. And we simply asked, are they correlated? Is the reactivity of your dopamine system predictive of your willingness to expend effort? And we found that both within the striatum as well as within ventromedial prefrontal cortex, really orbital frontal cortex, in fact, in both of those cases we found that people's reactivity of their dopamine system predicted their baseline willingness to perform effort. This actually raises sort of a general question. If we're looking at patients who aren't willing to expend effort, who show low motivation, would a dopamine manipulation be an appropriate treatment? In general, one's sort of hesitant to go this direction with most patients, particularly amphetamine, which can be addictive, obviously. You think twice before you start just saying, I'm going to go give amphetamine. You could say, well, what about D2 agents? We know if D2 blockers will cause people to show poor motivation. What about D2, D3 agonists? We can do that. There's a troubling issue, though, that comes up in the Parkinson's field, where we routinely give people D2, D3 agonists, and there's a percentage of subjects who start to develop more compulsive sorts of behavior on it, and so you're a little bit cautious about thinking about that as well. I've recently become extremely curious about the possibility of doing this with some of the new D1 agents. And here's why I would think about a D1 agent. If you look in mice, if you look at mice who are lacking D1 receptors, genetically they've had them removed, they show very low willingness to expend effort. This has been shown not with the sort of Salamone task, but with just sort of progressive ratio, fixed ratio sorts of tasks. What's interesting is there are some really new D1 agents, selective agents that are being tested. None of these are currently available on the market yet, but there's a partial agonist, havapodin, which is being used in Parkinson's trials right now. Eli Lilly has a new drug, mevidalin, which is a positive allosteric modulator. If you don't know what that is, it's not a surprise because these have not been a staple of pharmacology. But what this is if you've got a normal agonist, it would bind at a receptor site, what's called an orthosteric site, which is where the actual receptor is. But these allosteric sites are not the receptor, but they're essentially connected to the receptor, and they up or down regulate the reactivity of that receptor. What's cool about that in this case is it means you're not just sort of flooding the system and having activation just sort of all the time there. It's just going to enhance the activations when the endogenous dopamine would be released. This is really critical in the dopamine system because dopamine, some cells have a sort of tonic activity. There is a tonic, just small amount of dopamine firing going on regularly. But the real juice in the dopamine system is what's called burst firing, where you will get it when something stimulates the system and it will release a whole lot of dopamine briefly, and then it sort of shuts back down. The dopamine transporter pulls the dopamine out again. And so you've got these periods of intense increase and then stoppage. That's where the juice of dopamine really is. And so you'd think that this sort of modulation might actually be a great way to do this, and it would be much less likely, though, to have sort of sensitizing effects because it's the person's own endogenous dopamine, also much less likely to have the sort of rapid rush that you can get from cocaine or amphetamine. This is going to be something that's really tied and synchronized to the person's actual system. Very eager to be able to actually try this sort of out. If I can get Eli Lilly at some point to release the drug. They don't currently have an investigator-initiated program with it, though I'm trying with them. So I want to switch gears a little bit, because so far all I've been talking about is physical effort. But of course, and I've got a room full of academics here, a lot of what we're challenged with is not physical effort, it's cognitive effort. I mean, every time you've got a grant to review, or a grant due, or a talk to write, there's a decision about expending that cognitive effort. One of the people who's really looked at this is actually one of our new recruits who will be joining us in the fall, Andrew Westbrook, who developed a task called the COGAD, which just stands for Cognitive Effort Discounting. And the way they did this was their manipulation is just working memory. How many, if you're doing an NBAC task where you have to essentially say repeatedly whether a letter was the same or different from a letter that occurred some number back, you can increase the effort demands simply by extending the number of steps back you have to go. So you can go from an easy 1 back to, for me at least, a nearly impossible 6 back. I simply do not have the working memory capability to perform that level of effort. And what they would do is they'd first get people to do, familiarize themselves with what those will take. And then on each trial, they have to decide whether to do a simpler, easier number of letters back or a harder one for much money. Andrew, being a little bit more sophisticated than me, immediately realized that he could probably do this more efficiently if he did a sort of titration scheme where on each trial, whether you decided yes or no, or hard or easy, determines what that next step is, and so he can very rapidly titrate to the person's essentially indifference point in terms of decision making. And he's since gone on and shown relationships between cognitive effort and dopaminergic variables. He's also shown some interesting data where he has people doing the task and doing eye tracking while doing it, and he'll measure to what extent their gaze at different things like the reward value, the effort level, how much that drives the decision making. One of the other things that becomes really apparent, though, if you spend some time thinking about effort, is the issue of fatigue. Because effort is not static, it's changing. It changes for you across the day. How many of you have the experience where you're working on something cognitively and your just brain feels tired to you? Like, I can't think any further, which is sort of a fascinating thing. We're all used to that with muscles and that physical soreness and fatigue, but we also clearly have this at the cognitive level. This has been modeled in these sorts of effort-based decision tasks. And interestingly, the models that are out there, at least for physical effort, often will, within a task, talk about recoverable and unrecoverable fatigue. The recoverable means if I just have a pause, if I have a bit of a break, I can get it back again. Whereas the unrecoverable is I've just done this too many times recently, and I can't retrieve that within the time span of the task. I can retrieve that, tomorrow potentially, but it's not there for me now. There's also been some really interesting recent attempts to actually try to quantify effort based on brain measures. So rather than quantifying effort objectively on the level of here's what you have to do, how do we measure effort in the brain? Can we quantify that? And if you think of this way, like Shenlov has, just define effort, which very sensibly, as the process of overcoming the cost of departure from automaticity or rest. So if you think of it that way, you can say, well, what are some neural measures of rest? So for instance, it's been known that alpha activity in terms of EEG signals is essentially higher at rest and goes down as a brain area becomes more active. So you could do something like measuring that. There's also some work based on some fractal scaling math that I admit I don't really fully grasp all the details of the math, but the one way to look at it is that when you're at rest, a neural system or any system can be easily perturbed. The network itself is highly flexible in that situation. So I'm at rest, something happens, my brain just goes straight to that, easily distracted by it. In some ways that can be quite adaptive in that flexibility. On the other hand, when you're working hard at something, you need your system to actually resist those sorts of perturbations. You need to be able to lock on. And so using this sort of math, they've been able to say, well, across different sorts of conditions, do we see this sort of manipulation, this change in terms of brain? And they've done this in several different ways, including situations just of task difficulty or complexity, the novelty of it, how if it's not, automated for you yet, it requires greater work. But also just with aging, that for older folks, sorry to say, particularly as we get more elderly, we end up often having to actually work harder to accomplish the same thing. And in all of these cases, we can see correlations with these sorts of scaling factors that happen in terms of the perturbability of the system. There are some interesting peculiarities, though, that come up with effort. From an economic standpoint, you usually go, well, effort is a cost. So you should not choose to perform effort unless the rewards are really high. Yet we know that humans often go and seek out effort. They do things physically for reasons of some enjoyment in the activity itself. You know, yes, there are people who go run and jog because it's going to keep them healthy and in shape, or they're trying to win something. There are a lot of people who do it, though, just because they enjoy the actual activity itself and are choosing to expend effort. Similarly, I mean, I don't know how many of you do Wordle or, you know, all these things we do as puzzles and things that work our brain, and we do it out of and enjoy it, which you wouldn't expect within a simple sort of economic model. There are clearly other things going on here, and we will see this in some of our tasks, where it's like the person will choose the harder task because they're like, well, I'm going to challenge myself, and it, of course, changes the metrics we're looking at, because there's some of these folks who simply will not discount because they'll take everything as a challenge. So what I've tried to cover is just give you guys sort of an introduction here to this line of effort-based decision-making, discussing a little bit of how we've tried to operationalize it, how we've been able to link it to dopamine functioning with ways that have a lot of congruency with the animal studies. We've looked at this particularly in major depression. There's also a literature that's developed on these tasks within patients with schizophrenia, who interestingly really struggle in terms of using reward parameters, probability parameters, things like that, to adaptively adjust their decision making about that effort. I've presented a little bit here on some of the computational models of how they've allowed us to get a little bit nuanced in our thinking about what's going on here, and just sort of introduced a couple ideas regarding some individual differences and things like fatigue as they may play in here. And I have to, for all of this, express my gratitude to my collaborators, but particularly Michael Treadway, my former graduate student, who really launched this work in the lab when he was at Vanderbilt with me. And then, of course, funding, which has been funded by both NIMH and NIDA. Thank you. Questions? Yeah. Yeah.
Thanks. I want to go back to something you said early on about some of the patients with depression, their discounting kicking in almost immediately.
Yeah.
I can totally see why it's in one sense healthy to not let it kick in immediately, but from lots of perspectives about rationality, there's something irrational about having a break point where you would start letting it kick in. Right? You're going to be susceptible to all sorts of doing nasty things to you if you did that. So I just wonder if you had anything to say about, say there, if this is, as it were, depression being the pains of rationality without a block, or is there something else going on there?
Yeah. I mean, because you actually, you remind me of something that does sometimes show up in terms of depression, where there are some situations where patients with depression show a more accurate perception of certain situations that relative to normals, the healthy individuals who will be overly optimistic in certain evaluation. And so one could look at it like that, and one could even say, look, if the effort really feels significant at a low level, then it, for instance, if you're so fatigued, then that cost kicks in immediately. And so within that perspective, it may be quite rational. I would say, though, it's still incredibly limiting if that's the case. And we know that anhedonic symptoms, which unfortunately often conflate between both willingness to expend effort or motivation, as well as the actual experience of pleasure itself. But that constellation of symptoms is, in depression, ends up associated with higher suicidality and greater functional impact. And unfortunately, it's also traditionally been harder to treat because both traditional cognitive behavioral therapy as well as traditional antipsychotics, including the SSRIs, have had a harder time treating those symptoms. And in fact, those who have, individuals with depression who have those symptoms, have a overall worse prognosis than folks who are depressed who lack those problems. And so, yes, I think you're right, there may be a rationality to it, but it's really limiting if that's the case, if everything feels like that much work to you. Whereas I would argue the normal state of being should be that things that don't take much effort, we should be willing to do fairly automatically.
And your very last point then also suggests that there should be some things that are very, very high effort and you take it to be within full bounds of rationality. Say, hey, that's good too.
Yeah, well, there is this thing that comes out actually in society where we really, really value those folks who are super achievement oriented, who are really willing to just work hours and hours and hours and put in that effort. We value that, we praise it. I mean, I can't tell you how many movies or stories you can get into about, that prioritization and sort of merit view of people's work to get to that level. Yeah. And we academics are, totally susceptible to this often, given the hours that many of us keep. And there are problems that come with that as well. And of course, one of them being burnout. Yeah.
You could really manipulated the action of the reward. The reason I'm asking this is that presumably healthy people, if make the reward big enough, the effort will go way down. Because it's what we call a substitution of income effect. So it'll go down. I'm just wondering if schizophrenic, I don't know, other depressed people, would their effort go more if the reward were higher? The healthy ones will go up and go down. Eventually,
yeah.
Eventually,
yeah.
not at $2.
Yeah. So we have not pushed that boundary. I will say one of the things that we have done, and I was always a little bit nervous when we initially introduced the effort task, was the fact that we were not actually manipulating across trials the effort level itself. We were manipulating the reward and probability or the subjective value. For the computational modeling purposes, it's actually really valuable to have multiple levels of effort in there, so like a low, a high, a middle, or even to have the effort level varying parametrically. And for instance, other techniques we've worked on a little bit have been more willingness to pay models, but willingness to work models like that. And so there are certainly other ways to parse this space up that allow us to get at some of that. But we haven't tried what you're looking at. But there is one point I do want to make, which is really interesting, is that there is some data showing that within some of the reward network, you will see greater responses to the receipt of the reward if you had to work harder for it. So if you've invested...
Same reward.
Yeah.
Parents were right all along.
And, I think of that a little bit just like in sporting events. If you win the game and you have to work harder to get there, it feels more rewarding than if you won the game and it was easy to get there. And I wonder about how that may play in. That was not something in my own naivete when we started this that really occurred to me because we were just thinking of it as this sort of, simple cost reduction, because we were about the decision-making part, not the end result of the actual receipt of the reward when you were receiving it. Yeah.
So, yeah, related to that, do you think that people are aware enough of that effect, that at least some participants who choose the harder task, thinking like, it'll be worth it because it'll feel better and it'll make the reward feel better?
I don't know. I do know, though, that there are some of those subjects, though, who perceive it all as a challenge. And I remember doing a study here. We were trying to actually get at a little bit of the fatigue modeling. And we had someone who was an athlete come in. And I mean, I was interested in actually these breakpoints. At what point, like in a progressive ratio test, would people give up? And she just kept pushing and pushing and pushing it. And I was, what's going on here? And I talked to her afterwards, and she was just like, well, I just treated it like a training session, and I kept seeing how far I could go with it. So in that case, I don't think, like she was saying, I'll feel the reward better if I do that. I don't think that was it as much as this sort of, I've created a new challenge here, and so it was more of the competition with herself than the reward that was being given, which, those little sorts of ways of approach are, the bane of every cognitive scientist, and people try to do things in ways you don't think of. There's a question back there, yeah.
Yeah, so I was wondering, what's the, how does, effort, he connect to, concept, cognitive resources that my lab is also very interested in. And I was wondering, how does that relate to, the difference between control and the depression, because we can imagine because there's individual differences to, cognitive resources. If someone with, limited cognitive resources, they might perceive the same task to be, much more effort costly.
It's a great point. I would assume that is the case, that someone with lower cognitive reserve would end up perceiving some of this in a harder fashion. I think one of the things that's interesting is whether we can capture that in some of the sorts of measures of effort in terms of the brain signals, and that's an open question, I would say. I had another point there, and my own cognitive effort derailed me. Yeah, I lost what my point was. Too easily perturbed in terms of well, I'll come back to it if I think of it.
So I have some results from years ago, which I'll send you, the paper about gaze patterns and people's choices of where to look are depending on effort in a very surprising way. It was basically looking at things that aren't immediately in view, but you know they're there. But it raised all these questions. For example, these decisions are being done on the sub-second level. So you're not thinking about effort in the same way, and it may be very different mechanisms, or as you would when you're really investing in one task. So in this case, when it's a short time scale, which I think really goes to some of the points on it, is you're debating at any given second. You've got to be monitoring. If I'm not doing this during this quarter-second interval, I really could be thinking about what I'm looking at rather than where I'm looking. So that means we may have these systems that are always computing the trade-offs, and who knows what the costs are at any given second. But if you don't have the system computing the trade-off, you're in bad shape, because then you're going to lose over the long run. So really important questions that don't get enough attention.
Fully agree. And how these things are actually being integrated over time is interesting. I didn't present it, but there's an interesting study about Isabel Berman, who is currently a postdoc at Princeton in the Yale lab. They were actually using the effort and asking whether you could predict relapse of depression, recurrence of depression, if people were being withdrawn from their antidepressant medication. And their effort level on her test was not actually predictive of this. It predicted whether you had for the depression group or the controls. They didn't predict that outcome. What predicted the outcome is actually the amount of time that it took people to make the decision. So there's this integration over time before they would act. And that was actually turned out to be predictive, suggesting that some aspect of that integrated process was still slow, even if they were willing to make the decision to perform the effort, which I found interesting. Yeah.
Piggybacking off Irene's point is the question of fatigue is something that I find really interesting because to some extent it's not really analogous to like muscular fatigue because it ultimately seems to be the case that if you're mentally fatigued, if you get the right incentive, you can just jump back in with no problem. And maybe like the worst manifestation of that is when a deadline is coming up and now like the thing that would have fatigued you 2 weeks ago, you can go all night. And I think there's some research suggesting this sort of like constant monitoring for available alternatives, where like if it's 2 weeks in advance of the project and I've been working on this for 15 minutes, is there anything in the world that I could pivot to? That would be worthwhile. Yeah.
Well, I learned that my whole career by doing productive things when I was avoiding doing the thing that I should. It actually, the modeling of the key with recoverable versus unrecoverable, part of that whole model of the recoverable fatigue is simply if I increase the incentive value, will they then actually go back up again and be willing to perform that effort? And so there's part of that fatigue which is clearly recoverable in that sense. Whereas there are other aspects of it which is just like, I just don't have the juice to do that right now. And so that distinction, I think, is probably extremely important. One is really tied, most likely, to that incentive motivational component, where the other seems to be tied to the resource being depleted.
I could follow up on that.
Yeah.
I have a different question, but I'm going to follow up on this. So this idea of depleted resources, that struck me when you were comparing the effort levels for depressed versus control, right? The depressed folks, they also had to get up in the morning and get out of bed and get there, right?
Yep.
They might be rationing their effort for making it through and getting home. And so I was wondering, how do you factor that in?
Yeah, I will say we haven't factored that in truth. We've almost always treated this as just, this snippet within the lab, not really bringing in what's going on outside of it. One way to potentially bring that in is actually trying to move more to studies outside of the lab, using experience sampling sorts of methodology. We've actually done more of that on the opposite end of this, which is more on the urges and ability to resist urges than we have on this sort of low end of unwillingness to expend effort. But that might be a way to start to try to do something that would be a little bit fuller.
Yeah, I like that.
I mean,
it gets to the sort of rationality question, right? What's the time scale of rationality?
Yeah.
If you had a different task for a human who was non-depressed, and the choice was expending effort to get a reward or doing nothing, what percentage of humans do you think would pick nothing?
Yeah. So at least in the briefer time span, we definitely do get a situation where some people will choose nothing. Where it shifts, though, is as we lengthen that time, because then you get into boredom. And we have, done these things where it's like, you can finish, when we were playing around initially, we had some variants where it was like, okay, well, the difference is you can finish this thing in like 7 seconds, but we didn't want to then mean that, you're going to move on to the next trial immediately. So you just had to then sit there for the next 20 seconds, which you would have spent doing the other task. And of course, that starts to change the equation here. as we incorporate those temporal factors.
Another one. Okay. All right, now you have depressed people, so
Yeah.
you're going to expect them to choose nothing more often. Right? If you have a choice between nothing, or either your high effort, high reward task, or your low effort, low reward task, which more tasks do you think a depressed person is going to choose more often, and as an alternative to doing nothing?
Well, as the alternative to doing nothing, they're going to choose the easier task. Given, though, the choice of doing nothing, you're also going to get a significant number of those choices to do nothing. And the reason I'm confident about that is this issue of even at the lowest effort level, where you're getting that effect immediately, means that even what we're considering the low effort option is still being considered as effort. And so even then, since that discounting's happening immediately, it means there's going to be more of that time where they're just going to say, no, shut down entirely, not do anything here.
So I'm very sympathetic to this issue of covering the parameter space.
Yeah.
I have these models, you've got discounting happening at the very lowest levels and things like
Yeah.
that. And it got me wondering about what would like less than zero effort be? And that the answer is help, right?
Yeah.
So I was starting to wonder if there's any way to work in, probably not with the tapping task, some sense of degree of help or assistance, because that does seem like it could be ecologically relevant in some ways.
Yeah, to tell you the truth, I've never even thought about that issue in this space.
Something like that, exactly.
I couldn't hear you.
How much are you willing to pay for help?
Yeah. Where you could, you could even do it where, since we've already got them winning money, that you can actually take your money to avoid having to do the further
How
work.
much are you willing to be paid to turn a high task into a low task?
Yeah. That would actually be doable experimentally. It's a really interesting idea. We can start a collaboration and see.
Any other questions?
Yeah.
Most of these were just behavioral methods, right? Do you have any imaging data on these effort-related cases?
You do have imaging data on this, and I didn't really present it. We never actually published much of the imaging data, and basically this would be that scoop and then didn't really, even though we should have done it, I think, motivate the person working on it. Unfortunately, they didn't get enough incentive for them. We do see there's certain areas that their level of activation is predictive of the willingness to choose to do that other task. Particularly at engagement, for instance, temporal striatum seems to provide some predictive value there in terms of whether they're willing to do the task. One of the things we did do this with depressed subjects as well in the magnet. We had to do a fair amount of titrating to get enough trials where they would choose to extend after and those that they wouldn't. You do see this sort of network that includes the ventral striatum, nuclear cilia, and then you do a confined children for
And for those that is always seeking a higher effort, can those also tone down?
So if titrated properly, yes. It is really important for those individuals that you not just go in with like a stop level, but when you set those boundaries for the individual person, so doing that both in terms of rewards level, but also what the work level required is. And what we now do when we do these sorts of studies is go outside of the scan and define what the person's indifference point is in the decision making. And then so when you come into the scanner, you focus around their indifference point rather than just going in and presenting the same thing for every person. Because we found that otherwise we get subjects where it's just like, yeah, they just chose to do all of it or to chose very end of it, and you wouldn't put enough trials to do the analysis, and so that titration has become standard for us. And in fact, if we ever move forward with those one manipulation studies, we don't necessarily at baseline get those indifference points. Then we come in and just do the manipulation so that we focus on that.
Okay, thank you very much.
Thank you.